Okay, so it's my pleasure to introduce Karthik Ganapathy from the University of Michigan, and he'll talk today about equivariant commutative algebra and positive characteristics.
Yeah, thanks for the invitation, and thanks to Nate for inviting me here. So let me start. And so my talk is somewhere in the middle of like commutative algebra and representation theory. So if I write something, I might not necessarily define it, but I'll like tell you how to think about it and like give quite a few examples as well. Okay, so I'll start. So let S be the ring which the infinite variable polynomial ring, which I think most of us have seen because it's the first example of a non-noetherian ring that we've seen. If you take the ideal M equals, this is not finitely generated. Okay. Now I'm going to write S as sim V, where here V is just the vector space with bases like E1, 2, and so on. It's a big, it's K infinity, but a countable infinity, and I'm like prescribing what the basis vectors are, and I'm identifying S with the symmetric algebra of V. So note that when I write it this way, it's clear that GL-V acts on S. Okay. So I want to start with a fairly easy observation. Ascending chain condition holds for GL stable ideals in S. So, and here S is like, I mean, I'm using C for now, but I'll switch to other fields later. So does anybody see why this is true? It's not that hard. And by GL, I mean GLV.
Not that many.
Yeah, there's not that many of them. And so, okay, so let's okay, so the maximal ideal M, this is stable under the action of GL. Okay. And so there are also the powers of the maximal ideal, and then there's the zero ideal. Right. So there are some obvious ideals that I can write. So there's the M to the T with D in it, and the zero ideal. And I claim that these are all the ideals. So let I be, so let me just like write the proof quickly. So let I be a GL non-zero GL stable ideal. So whenever you have like the general linear group acting on it, there's like a torus inside of it. So every ideal and everything that we talk about will naturally like carry a grading. So in this case, I will be homogeneous. So take F in I of smallest, F in I homogeneous of smallest degree D. So that means that F is in sim D of V. But the point is that sim D of V is an irreducible GLV representation, which means that since I is GL stable, since F is non-zero and this in sim D of V, this implies I contains sim D of V. So I contains all DDD homogeneous polynomials, but this implies I is just M to the D. Okay, so in fact the only ideals are what I've written down here. From this you can see that ACC holds. Okay. So I mean this is a fairly easy observation, but we can kind of bootstrap this to kind of identify a class of S modules, which will also be noetherian in some sense. So let me define that now. Right. So I'm going to define a class of modules, and again, right now I'm just working over the complex numbers. So GL equivariant S module. So M is an S module. Along with an action of GL. That's that. So the data is, you have it's an S module to begin with, and it also has an action of GL. So these are both data. And then you need to have some compatibility criteria. So that's first, G of S dot M equals G of S times G of M for all G and so what it is saying is that the map from S tensor M to M is GL equivariant map. And so GL again is a huge group. And if you're just saying that it has some action of GL, it's like too restrictive. So you want to say like that M is a nice GL representation, which is what criterion 2 is. And then when you decompose M, when you write M as a GL representation, you have an isomorphism, like direct sum of like S lambda of E with some multiplicity. And so here S lambda is a Schur functor with highest weight lambda applied to E. And if you don't know what a Schur functor is, just think about examples like symmetric powers, exterior powers, and in general, like S lambda will be some interpolation between those two. And in the case S is itself like the direct sum of like S one row partition of P with multiplicity 1. And this is again, so I'm working exclusively in characteristic 0. So let me just say, yeah. Any questions about the definition?
So the second thing is a finite description. So you have finite multiplicity spaces.
Right. So yeah, sorry. So and a priori, no. So n lambda can be in like n union infinity. I'm just saying. It's just it's yeah. Does that make sense? Yeah. I'm not saying it's a finite.
Polynomial.
It's a polynomial. It's like an algebraic condition for the representation. Yeah. Okay. So now there's a way. Yeah. So there's a theorem that I want to state. And this is due to Snowden from 2009 and also Church. Oh, let me also say something else. So when you have a GL equivalent module, like so as Nate was like alluding to, a priori again, like every a GL equivalent module can be just like completely unwieldy. Like you can just take an infinite direct sum of S, that would be a GL equivalent module. But you want to impose some finiteness criteria. And so I'll say that so a GL equivalent S module. So whenever I have that, I'll say M is finitely generated. And again, it's finitely generated as a GL equivalent S module if there exists M1, M2 till MR in M, such that M is generated by the orbit of all these Mi. So by G dot Mi with G and GL, 1 less than equal to X. So again, here you don't require that it's finally generated as module, but up to the action of the group, it's finally generated. And all the all these things like M to the D, 0 is clearly finally generated, but M to the D again is finitely generated by like X1 to the D. Because usually generally in a group you can just get every other monomial that way. And that's precisely what this theorem is going to say. And it's like a Noetherian itself. So let M be finitely generated GL-equivariant S module. And again, case C here. Every GL stable submodule will be naturally a GL-equivariant module. Is also finitely generated. And I want to prove it, but the proof is not that difficult. Like the idea is that you want to so take something like S tensor S lambda of V. These are all going to be finitely generated, by one tensor, the highest weight vector in S lambda. Because using the GL, you can get every element of the form one tensor like V, and then using the action of S, you get everything else. So this is finitely generated by one tensor V, where V is any non-zero vector in S lambda of V. So what you do is you use like what's called theory's rule to show that all partitions that occur here have at most like some there exists an n such that all partitions that occur in this is at most like n. And then you can show that this is finitely generated because you can kind of restrict to the finite variable case. That's kind of the idea. I don't want to say more than that. In this, even in this case, for example, like the fact that you have only m to the d and 0, you can just see it by going to C and join x1. And that's kind of a key idea here as well, like where by theory's rule, you can just bound the number of rows that occur in all the partitions that occur here. And you can just go to a finite variable case and use like the classical Hilbert basis theorem. Any questions or comments? So yeah, this is not like completely trivial, but it's not that hard. Okay, so now you have once you have like a Hilbert's basis theorem like situation, the next question to ask is there a Hilbert's G like theorem in this setting? Now, what can you say about resolutions of like S modules? And it's so Hilbert's G theorem says that if you have an n variable polynomial ring, the projective dimension is of any module is at most n over the n variable polynomial ring. And you can see that in this situation that kind of fails quite easily, where projective dimension of like most modules would be immediately infinite. So let me give an example. So if you take M to be C, then you can write down the if you take M to be C, then you can write down the resolution of M as an S module. And it's called the causal complex. It's a pretty common thing where you write. So yeah, when I say C, I mean it's S mod M. So whenever you go modulo an ideal which is like generated by algebraically independent elements, you can write it's a very canonical sequence, canonical resolution called the causal complex. And let me just write that down. So it's the first element would be you're killing the maximal ideal, and the maximal ideal is a copy of like V inside S. That's it's sim 1 of V. And then you want to it's a S for your resolution. It keeps on going. I mean, see, all of these things also exist in the finite dimensional cases, but in the finite dimensional case, like wedge n plus 1 is 0. It will be 0 from there. But in the infinite variable case, it won't be. It will never vanish. So Hilbert's G like theorem phase where you're just like trying to compute the projective dimension. Almost all objects will have like infinite projective dimension. So there's another invariant in commutative algebra called the regularity. And so I'll state another theorem. So here is a theorem due to Sam's Norton. So it says that let M be a finitely generated GL-equivariant S module. Again, we are working over C for now. Then, so it's a two-part regularity of M, and I'll explain what regularity is in just a second. Is finite, and each linear strand in the resolution of M is finitely generated GL-equivariant module over the exterior algebra. So it's like a causal duality statement. So let me now explain what this means. So whenever you have a graded module over a polynomial, let me first explain what this means actually. So whenever you have if M is any graded module over like over a standard graded polynomial ring, there's something called the Betti table that you can draw. So you get like a table where so it's 0, 1, 2. And this table will like encode things about the resolution. And the way you do it is you take the ijth position here will have like the I tall group for S. But with everything has a grading, so it'll be the I plus jth graded piece of tau I. And that's like this weird normalization. And I'll like give this example. So in the case of C, what this is if you take M equals C, the Betti table will just look like this. It'll be C, be wedge 1 of C, wedge 2 of C, and so on. So their theorem says that if you give me any finitely generated GL-equivariant module over the variable polynomial ring, the number of rows in the Betti table will be finite. That's what finite regularity means. So there will be finitely many rows where it will be non-zero. And each row, which is what this linear strand means, can be given a structure of like a module over the exterior algebra, and it will be over a GL-equivariant module over the exterior algebra, and it will be finitely generated as such. So in this case of the C, you can, this, if you just take the direct sum of all of these, it's just going to be the exterior algebra itself. Oh, sorry, not sorry. Yeah, that's right, thanks. So it'll be exterior algebra itself, but for an arbitrary module, it will be, it will more often than not have multiple rows non-zero, and each row will have the structure of like a module over the infinite exterior algebra. Again, there's a corresponding statement in the classical like n variable case as well. And in that case, it's like not that hard to prove, but in this case, it's kind of fairly surprising that if you restrict to this, GL-equivariant modules, the classical like causal duality statement holds. Okay, so this is like a story in characteristic theorem. And when you are talking about like things like Hilbert's basis theorem and Hilbert's SG theorem or like causal duality, the characteristic of the ground field like rarely matters, but in the classical case. But in this case, we have kind of cheated and we are like working with like general linear group representations of GL. And we do know that when we in the representation theory side, of course, if we go from characteristic 0 to characteristic P, things change a lot. So the question is like, how does that change things for us? Like, do the same result, do noetherianity hold, does noetherianity hold, does like this causal duality type statement hold in characteristic P? Or if it doesn't, like what can you say? And so let's try to let's try to recreate most of what we did in over the complex number to characteristic P. So immediately, like when we try to prove noetherianity for just the ring, we use the irreducibility of the symmetric powers. But there itself we run into an issue. So yeah. So here from now on, we'll be working with K, an infinite field of characteristic T greater than 0. So in this case, one problem is that sim E of P is not irreducible if D is greater than or equal to P. The Schur functors, in general, like when you have some representations over, like characteristic 0, when you reduce mod P, it tends to not be reducible anymore. And in this case, like if you look at like sim, so if you take like W to be the P powers, this is a subspace of sim P. And it's in characteristic P, when you like apply G, like a group element on x1 to the P, you first apply it on x1 and then raise to the power of P. But in characteristic P, like when you a plus b the whole power P is a to the b plus b to the P. So G dot x1 to the P will be also in this. So this is a GL stable. So W is GL stable. Yeah, this exactly. This is what's called the Frobenius. Yeah, I mean, this is what it's usually written as.
It's not our algebraic groups class today.
Okay, yeah. So yeah, that's the thing. The problem is, in fact, these Frobenius twists that happen. And so, like now what happens is that this implies that there are a lot more ideals in characteristic P. You have, you not only have like m to the d, but you can take the ideal generated by the xi to the P, or more generally xi to the P to the n, which is usually written as, it's called the Frobenius powers, and it's written this way. So here it just means like the ideal generated by, you take the whenever you have I to this square bracket P to the n, you take a generators of I, then take all of them to the P to the n in characteristic P. And then you can take their sums, their products. There's a lot more you can do here. And so it's not going to be very easy to like classify the ideal lattice as we did in characteristic 0. But still this result holds. And that's because of a much earlier result actually of someone from Cohen from 67. So this result, again, now again I'm S here, and there's a definition of a GL-equivariant module where it's going to be what's called a polynomial representation. I don't want to define it now. But if you take such a module, every GL stable submodule is also finally generated, and that's due to Cohen in 67. And it was like rediscovered by Ashen Thunder. And well, they in fact do a much stronger result. They prove that if you do this whole story with like just not GL but S infinity, the infinite symmetric group. So if these are the permutation matrices in GL, they show that there's a similar statement that holds. So that in particular would imply that. And that situation is like much harder. Like you can't, it's not even easy. It's like, it's very, very hard to, for example, classify just radical ideals which are stable in the action of the infinite symmetric group. And the techniques are like very commutative algebra. It uses like Grobner theory to prove that statement. So the noetherianity still holds, even though it's like not easy to like classify all all submodules or in characteristic P.
I have a question. So in the finite case, the composition factors of sim P are actually known.
That's right.
It's given by like these Curie patterns. So do you know what the composition factors are in this infinite case?
So if you know what it is for like for sim D, if you know what it is in like K to the D, then it's going to be the same.
Okay. All right.
So
you can just use those. Okay.
Yeah, it's just the composition factors will, again, it's like you write some periodic
Yeah.
type stuff, and you get it. Yeah.
So it's due, actually, Steve Doty actually proved it in his thesis. That's from his thesis.
Okay. I did not know that, but yeah, but I'll say that will still not give you all the ideas, because you can again like I think you can take, like you can do like m to the p minus 1 plus, sorry, you can do m to the p plus m to the p plus 1.
Okay.
So that will give you, that'll give you a lot more. The ideas are still not even like, it doesn't directly follow from that, but it might be, it's probably not that hard, but like not very useful to do, I guess. Okay, so we now did noetherianity. So now the question is like, what happens with this, the causal duality type statement that we saw? Like, what can you say about Betti tables? Can you say the same thing? And let me just. So that's, and this is where things kind of get bad. So now instead of now you can take, yeah, so the question is like whether if you take a finitely generated GL-equivariant module in characteristic P, I think there are two parts to that result that I just erased. One is whether they're containing like finitely many like rows, and whether like each of the row you can put some structure onto it. And the issue is again the Frobenius pass. So what happens is if you take the ideal generated by W, which is going to be m to the p. So let's try to resolve S mod m to the p. Now again, m to the p is generated by x1 to the p, x2 to the p, x3 to the p, and so on. And those are also algebraically independent. So you can write down the causal resolution for that. So the resolution looks like this. So it's going to be S tensor W. So W is a subspace here, this subspace. And then it's just going to be S tensor wedge 2 of W. But unlike in the case where we started with like S mod M, where it was C, W has degree P. So W has degree P, which means when you do the ith exterior power of W, this will have degree P times I. So when I write the Betti table for this, it will look like this. So beta of, and so this thing is called beta of M. So beta of S mod M to the P. So 0, 1. So in this case, it will be here. But in the for the first, for the first of the G, it's this one. It's in degree P, which means because of the normalization, it will be in like P minus 1. And the second place, it will be in 2 times P minus 1. And so on. So in the for I, it will be at I times P minus 1. So when you go to the infinite case, it won't be contained in finitely many rows. It will keep on like jumping from these. Yeah, we go like this. So that essentially means that like the finite regularity result does not hold in this case. Okay, and that's because you have algebra, you essentially have algebraically independent elements in sufficient, very, very high degrees. Okay, so this is what now I prove. So I want to say what you can say about the Betti table. Theorem A is, and I'm going to state fairly informally. So let M be a finitely generated GL-equivariant S module. The non-zero entries in theta of M, which is the Betti table of M, is contained in finitely unique lines. So, even though you can't say it's contained in finitely many rows, like in this example, if you look at it, it's contained in a line of slope p minus 1. So more generally, what will happen is if you take a module M, so the beta of M will look like this. And outside these like finitely many lines, it will be 0. Okay. And I want to say how I want to like state another like structural theorem which implies theorem A. So theorem B, and it's about the derived category. So here let mod S denote the category of GL-equivariant S modules. The derived category, so the bounded derived category of. So by this I mean it's all it's all complexes where the homology is only contained in finitely many places and it's finally generated. Okay, so dB is this, okay. Let me first read it so then it will be clear. dB mod S is generated the triangular category by so yeah, so I'm giving some explicit generators with the derived category. So I'm saying that the derived category is generated by the modules S and S mod M to the Q. And you can also like what you can do is you can take S tensor V or S mod M Q tensor V. You can just like take some infinite direct. Essentially, these are from the point of view of commutative algebra, there is like infinite direct sums of these two modules. Is the statement of the so now it's okay. Now we've done everything to show why theorem B implies theorem A. For S is free, so it doesn't have any interesting way to things. But S mod M to the Q is it's going to be a similarly it will be like the Betti table of this module will be contained in a line of slope Q minus 1. And and what this result is saying is that if you give me any module, there is some exact sequences you can write with you can build every module out of these two classes. And so therefore, if you build it out, if some module is you need to take two of these, then it will contain two lines, and every module can be built in finitely many steps, so it will be contained in like finitely many lines. Is the okay? Yeah. So theorem B plus like causal computation implies theorem A. But let me say that like it's kind of it's a cheap way to prove theorem, because you're not actually like, again, the problem here is that the way that I proved the theorem, it doesn't guarantee, for example, that it's going to be like 0, non-zero, 0, non-zero, 0, non-zero in like one specific line. Because when you take some exact sequences, things could get cancelled out in like weird ways. And whenever you want to prove like that, it's always going to be 0 eventually, like all of these lines. What you would want to prove is you want to again like get an action of some like algebras on these lines and prove some finite generation result. And so I haven't, and I expect like, so what I expect is a line of slope q minus 1 will have the action of the like a line of slope t to the r minus 1 will have the action of the rth frobenius twist of the exterior algebra, but not being able to like prove any of, like I don't know how to define those actions. Any questions about theorem B? Okay. So now I'm not going to prove theorem. I mean, theorem B is fairly kind of difficult to prove. It's kind of what everything that I do kind of like leads to this result. But I wanted to now explain like how if you're a commutative algebraist, like what should you think about when you think about theorem B? And so let me state a very classical result from commutative algebra. So you should compare theorem B with this. So this is the existence of time cyclic filtration. So in this case, so let R be a commutative noetherian ring. So just a very vanilla noetherian ring that you polynomial, n-variable polynomial ring, power series rings, and things like that. A module, a finitely generated module, M, has a finite filtration, finitely generated R module. So 0. Such that mi plus 1 mod mi is isomorphic to R mod some prime bit. So this is a classical result about how if you have a finally generated, it's called people say it may be called Devisage or whatever, where you can just filter a module where the successive quotients are of the form R mod P. So the way you think about it is that if you have some like variety and you can prove things for the structure sheaf of like irreducible subvarieties, then you can essentially prove it for like all coherent sheaves. That's kind of what that's kind of one way to use this. So this result in particular implies that the derived category of if you replace mod S by mod R is generated by R mod P as P varies over all the prime ideals. Okay. Much stronger than this, of course. So this theorem is essentially a derived variant of this result of the existence of prime cyclic filtrations. But then of course you should ask like, how are these things prime? These are not even like radical. But the point here is that like in our setting, whenever you have a group acting on a ring, like the G stable prime ideals are not enough. And I want to like give a new definition of like what prime ideals are in this setting. And you will see that these are going to be precisely the prime ideals with that definition. Sorry, so this is a fairly like philosophical comment, not like any math as such. Okay. Okay, so So once I define this and like prove a small lemma, you will see why you should expect a result like theorem B, even without before doing anything. So definition, and there's also a fairly general definition. So let G act on a ring R. Ring homomorphism. So in our case, G is GL and R is the infinite variable polynomial ring. A G stable ideal I is a G prime if for all A comma B. So yeah, if I stop here, this is of course what a G stable prime ideal will be, but you only have to check this criterion for A and D, which are themselves G stable. So in our category, there's only like G stable ideas. Is the point for all A comma B G stable. So of course, G stable prime ideals are G prime because this condition holds for all ideas. But G prime ideas, there are potentially a lot more of them. So lemma. So in this case, like G equals GL, R equals sim B. The GL prime ideals are zero ideal. So the maximal ideal. So zero and the maximal ideal, these are both GL stable and prime as a normal ideal. But all the Frobenius so these are so the claim is that these are all GL prime and these are the only GL prime.
So this is stack quotient, right?
What do you mean?
Stack quotient.
I'm not trying to say, I'm not trying to say anything that way.
Okay, but I mean, I think it is.
Of what with what? What do you
With R with the action of G. So you can look at just like, G spec of a ring.
I see what you're saying.
So standard construction. Okay.
Okay, but okay, I'll give it
We'll talk later.
Okay, yeah.
Yeah.
So
One difficult thing is he's not talking about the infinite variable, this is the infinite GL. So it is a stack quotient, but it's for a like huge
Yeah.
uh,
I think it is.
but let me just let me quickly prove this so that you realize why working with infinite variable things are much nicer.
Yeah.
So let's just show. So I mean I'll just show m to the p. This is not too hard to do as well. So I'll show that m to the p is GL prime. Oh, and this is this is also equivalent to saying if f sigma g is an I for all sigma in G, then f in I or G in I. So the elemental criterion for checking if something is a G prime. So okay, so I want to show that the Frobenius power of m is GL prime. So let's take some elements f1 and f2 in R and assume f1 is not in m to the Frobenius power of p. And this means that there is at least one monomial in f1 which is where all the powers are less than p. So this means that f1 equals some monomial plus some f1 tilde, and yeah, where this monomial xi to the p does not divide m for all I. Because if at least one of the xi to the p divides m, then that then this whole thing will be in the. Okay, so now the problem is, see, when you just do f1, f2. Okay, so now it's given that f1, f2 is in m to the p. And so f1 times sigma f2 is in m to the p for all. Okay, let me is in m to the p for all sigma. So I want to show that f2 is in m to the p. Okay, yeah, sorry for this. Now the problem is, if you take sigma to be identity, the issue is that like f1 and f2 can, the monomials in f1 and f2 can like interact in weird ways and like cause cancellations, and like it's very hard to compute. But what you do here is take sigma to be a permutation such that f1 and sigma f2 have disjoint variables. So what you can do is like just take sigma to be something that sends 1 to 1000, 2 to 1001, 3 to 1002, and so on. So f1 and sigma f2 will just like not interact with each other, because f1 will have like the first 1000 variables, but sigma f2 will have variables all bigger than x thousand. But then when you multiply f1 with sigma f2, if that is in m to the p, that means that this monomial multiplied with everything in sigma f2 is in m to the p, m to the Frobenius p. But that means that sigma f2 must be in the Frobenius power of p, because there's nothing can cancel out m. That's the point. So you can just see any problem that you can create, you can just like push it away, and then like those will not be a problem. And the same idea, same thing shows that like m to the p to the n is all Frobenius are all GL prime. I have like 3 more minutes. Okay. So you can define what is the correct notion of a G prime. And in this case, it is these. And in characteristic 0, of course, it's only the 0 ideal and the maximal ideal. And in general, like, so something else that I'm trying to like now figure out is, what if you change sim v with something else? So an easy, whenever you're trying to analyze like these G-equivariant modules over a ring, the first kind of step is to classify or say something about the G prime ideas, so you can start guessing what things will be. So something that I'm trying to do right now is the kind of the next case after doing sim v, which is sim v direct sim v. So in this case, like you have R equals sim v direct sim v, which you can think about it as k adjoint x1. So in this case, there are so G, and again GL acts on this, but there are a lot more ideas. You can take like the 2 × 2 minus, that will be GL stable. There's just that you can create a lot more ideas in this even in characteristic 0. And the question is like, what is the GL spectrum of this? And in characteristic 0, this has all been computed by Sam Snowden. So in characteristic 0, the GL spectrum looks like this. So you have the 0 ideal. Then you can take alpha x1 plus beta y1 and then take their GL. So that essentially gives you a P1. So this is alpha colon beta. So it will be the idea generated by alpha xi plus beta yi. Then you also have the maximal ideal x comma y. And then this, you should think about this P1 having a generic point, which is the determinantal ideal. And y2 minus x2 y1. And this is kind of the spectrum, the GL spectrum. in characteristic P, so again, most of what happening, all of this argument shows that if you take x1, y1 and raise them to the p power, if you raise x1 to the p power and y1 to the p square power, those will all be like GL prime. So over this there's like a huge copy of n2 sitting corresponding to how you can. And here also there's a copy, alpha x1 plus beta y1 you can raise to the p power. And I've also shown that if you take these determinantal ideas and then take their p powers, they are also GL prime. And it's a bit harder, but I can do that. And so the question is, are they all the GL primes in for this? Like, do you get all GL primes from taking everything in characteristic 0, reducing them on P, taking the P powers and then doing like obvious kind of things that you can do with them? And are they all? And yeah, I'm not sure. Like I don't know. But yeah, I think I should stop here. Yeah.
So one thing that's sort of striking is that there's so few GL ideals, and it sort of suggests that maybe you could get some more geometric information by looking at like a smaller group. For example, you could look at like the union of the infinite union of all GLNs, and then you could look at ideals like in a VN, say, which would be sort of invariant under the restriction or something. I mean, it just seems to me that this group is so big that you're getting
So when you say the union of all GLNs, do you mean like as n varies?
Yeah, as n varies, but
So,
but there's some finiteness condition on the matrix.
but I'll say that like such finiteness condition won't help, because if you think about a polynomial, the polynomial only has finitely many variables. So every matrix in my world of this big GL, the action of any big matrix on these finitely many variables can be witnessed by the action of a small matrix in your sense.
No, I know what you're saying, but I guess what I mean is, I'm just wondering if there wouldn't be some variation. For example, one thing to the Lie algebra setting, you could have GL1, GL2, GL3 or something, and then you could sort of talk about, you still have concepts like a nilpotent matrix or a semi-simple matrix, even though it's this infinite union and it's defined in terms of some kind of ideals which are invariant relative to that. And you wonder if there would be some sort of, maybe what I said wasn't quite the right way to do it, but there could be something that could give you more kind of invariant ideals.
So yeah, I can also say one other thing, like when a lot of these things, it seemed like all I need to do is like use permutation matrices to do many things. And when you're only like working with like the infinite symmetric group, there is a connection between and this is work of my advisor and some of his collaborators, that there's a connection between like S infinity primes here and the Hilbert scheme of A2. So in general, like you can take a variety X, take its like infinite product, then you can try to classify like all S infinity subschemes or whatever. And there's a connection between like these subschemes which are like S infinity prime and the Hilbert scheme, and it's fairly complicated. Yeah, it's not like obvious, and there is more geometry, but I don't know more than that. Yeah, sorry, but yeah, there is something you can say that, and yeah, there are like there'll be families of things there and so on. Yeah, but it's the very less is known about the module theory side here. Like it's even the GL case is quite hard, so the S&P cases is much harder to like do any module.
Yeah, I mean, I just don't know. There's these various ways. I'm not really from like you have the infinite symmetric polynomials. Then you specialize them by setting all all the variables, most of the variables to 0. So I mean, one would wonder if there wasn't just some trick to somehow get a bit more, things happening here. That's in terms of the number of that you get, like just some ideals reflecting some kind of geometry in this situation or something like that. Like as I said, I think like the nilpotent matrices in GLN, have a lot of geometry with them, and so just something like that.
So one thing that is, sort of nice about this situation is that kind of what you're describing, you can't really fit into is. So we're requiring that the representations like this V is a polynomial representation, And if you want to get some more geometry, like say looking at the action of like the adjoint action on the Lie algebra,
Ah.
you really want to take something like V tensor V dual.
Yeah.
And that takes you out of this kind of polynomial functor world. And but once you do that, you see more of this type stuff you're talking about, but it also becomes much more complicated.
Yeah, it becomes an uncountable,
Even for representation, there is some sort of notion of like no codes, or like this stuff that's annihilated by the invariant polynomials, for example, in the symmetric part of the representation. So there is some even beyond the adjoint representation for any representation. But maybe for the adjoint, maybe it would be more interesting for something like, as you said, V tensor, V2 or something like that. Maybe
Yeah,
it's
so
very
that-
interesting.
The story there is very interesting, but also very hard.
Yeah, I mean, this is part of nothing.
yeah, okay, is there any other, yeah, so.
Is there anything you can say to replace G by the upper triangle and proceed?
I haven't thought about that case at all. Do you have anything, like if it's, well,
I don't know, I think it's. Yeah, I don't know what the right question would be.
yes, but it's a group, right? Yeah, it's
The BL, the B prime.
B. Yeah, I mean, I actually haven't thought about that at all. Yeah, that's a good question though.
A lot of this reminds me of monomial ideal stuff.
Oh, yeah, right, that's right, so, yeah, that's right, I mean. Yeah, I don't have anything more to say, sorry.
If not, let's thank the speaker again. Thanks.
So I want to remind everyone, we are gonna have dinner at 8 of India at 8. So